This lecture begins our studies of magnets and magnetic fields. We show to the left a compass needle pointing toward the North Pole. The north end of a magnet points toward the North Pole of the Earth. So the compass needle's pointy end is the north end of a magnet. The north end of a magnet is attracted to the south end of another magnet. So if we brought up a magnet in its south pole, the needle would turn and be attracted to the south end of this magnet. Magnetic fields are measured in Tesla, named after Nikola Tesla, the physicist. 1 Tesla is equal to a Newton per amp per meter. Some examples of magnetic fields. Earth's magnetic field is about 10 to the minus 4 Tesla. Earth's north pole is actually a magnetic south pole, since the north end of a compass needle is attracted to it. A scrap metal magnet, what you might see picking up a car in a movie, has a field of about 1 Tesla. The world record is held by the Los Alamos Pulse Magnetic Field Lab, and they have produced a field of 97.4 Tesla, about 100 Tesla. But the universe record is held by a neutron star, which can produce around 10 to the 8th Tesla. Here we look at magnetic field lines. Magnetic field lines indicate the direction a compass would point if placed at that position. So if we place a compass there, we see it points in that direction. Place another compass there, we see it's pointing down there. We put a compass over there, we see it points in that direction. Or we place one near the top, it points nearly up. The lines go from the north end of the magnet to the south pole of the magnet. So they come out of the north and go back into the south, is one way to think of it. Where the lines are most closely spaced, the force is the greatest. For example, at the face of one of the poles, you have a high density of lines. Attraction. Opposite poles of magnets attract. So the north end is attracted to the south end of the two poles. And if you look at the field lines, the field lines actually go from one magnet to the other. So it looks like attraction. Repulsion, like poles repel each other. In this case, if you have a north facing a north, you see the lines bend away from each other, or south facing a south, the lines bend away from each other. So lines from one magnet bend away from the other magnet, so it looks like a repelling. Well, there is no magnetic monopole. You can't get a north pole by itself or a south pole by itself. There's always a north-south pole pair. Anytime we try to cut a magnet down to a single pole, we just get smaller and smaller bar magnets. In this movie, we've cut a magnet in half, and it's being pulled apart. You see that after you cut it apart, the two ends closest to each other attract each other. You see the lines that are connecting one to the other. So it wants to be stuck back together as a single magnet. Originally you had a north-south pole pair. Now you pull it apart and you have two north-south pole pairs. So instead of getting one pole, you ended up now having 4 poles, 2 norths and 2 souths. It's also interesting, look, we flip that magnet that we cut in half around, so then the like faces are closest to each other, and we push them together. Here again we see the repulsion that we saw in the earlier slide. It's a nice example of the lines repelling each other.